Hi, in this lecture we are going to cover the rest of chapter 7, Alkenes, Structure and Reactivity. As you remember, in the previous lectures we started this chapter. We covered how to name alkenes and how to calculate degree of unsaturation. Then we have performed some exercises for calculation of degree of unsaturation. Then what we have done, we have covered the naming of alkenes. Further, we covered Cis-Trans isomerism in alkanes. As you remember, we discussed cis and trans isomers for disubstituted alkenes. When we have two substituent, the meaning of substituent is any group or any groups around double bond rather than hydrogen. We call them substituent. For example, in this case we have carbon-carbon double bond. This carbon on the left side has a hydrogen and methyl group. Methyl group is considered as a substituent, but hydrogen is not a substituent. So if the substituents are around carbon-carbon double bonds are on the same side like this, we call this is cis isomer. Or if the substituents are on the opposite sides, we call this is trans. This is correct for disubstituted alkenes. You remember we have another designation for alkenes, E and Z. If cis or trans designation is not possible, when it is not possible, if you have more than two substituents around double bond, what we do, we look at carbon-carbon double bond and we look at the substituent, and based on this you remember Kahn-Ingold-Prelog sequence rule, we assign higher priority and lower priority based on atomic numbers and based on the bonding. Then if the higher groups are on the opposite sides, we say this is E, meaning that they are on the opposite sides, antagon from German language. If the substituents higher ranked substituents are on the same side, we say this is Z isomer. As you remember, we covered these topics in the previous lectures. Then we discussed the stability of alkenes. We say that trans alkenes are more stable than cis alkenes based on the steric interaction of methyl groups on the same side. And we can understand this phenomena by a chemical reaction. If you hydrogenate trans-2-butene and cis-2-butene with hydrogen in the presence of a catalyst palladium, so basically it's a chemical reaction, you don't have to know the details of this, so we end up with the same product. If you have a heat of hydrogenation energy profile for these two reactions, as you see, the cis reactant, this one, has more delta G. This can be delta G or delta H. In this case, this is free energy change. Delta G of a cis reaction is more than the trans one. Why? Because the cis one has higher energy than the trans one. So we can understand also which one is more stable based on this experimental setup. Then we discussed in the previous lectures stabilities of alkenes. We may have various substituted alkenes. We can have tetrasubstituted, meaning that we have four groups, four substituents around double bond, 3, 2 and 1. It is found that tetrasubstituted alkenes are more stable than tri, than di, than mono. And what is the explanation for this stability order? It is coming from molecular orbital theory explanation. It's this: when you have a carbon-carbon double bond, if you have around alkyl, methyl, ethyl or any substituent, one of the carbon-hydrogen bond can be parallel to the 2p orbitals of carbon-carbon double bond, which they make here pi bonding. One of the carbon-hydrogen bond or sigma bond can be parallel to the pi bonding system, and we can extend the conjugation. Basically, you remember from previous chapters that when we have resonance, it makes it more stable by extending pi bonding through the molecule. So here the same concept applies for alkenes. If you have a double bond and if you have a substituent like CH3 or ethyl, methyl, propyl, anything, one of the carbon hydrogen sigma bond can be parallel to the pi bond, and this extend the pi bonding over the molecule, which makes it more stable. So that's the explanation for stability of more substituted alkene. Then we can basically solve a question related to this phenomena. In the first one, let's look at the question asks us, name the following alkenes and tell which compound in each pair is more stable. Basically, we have to look at how many substituents we have and how many substituents we have for these two molecules. Then we can compare. Let's look at the first one. I will redraw the first one so that you can see the number of substituents around carbon-carbon double bond. So let's write here A. We have carbon-hydrogen double bond here, this part, and we have hydrogen on this one, and we have a hydrogen on the other carbon of the double bond, and then we have this ethyl substituent CH2 and CH3. I am drawing this way so that you can see how many substituents we have. For this molecule, the only substituent around carbon-carbon double bond is this. So this is mono-substituted, or it has one substituent. Let's look at the other one. The other one has carbon-carbon double bond. It has here two hydrogen, and here we have one methyl and second methyl groups here, CH3 and CH3. If you look at this molecule, it has this substituent methyl and this substituent methyl. We have two substituent. This is disubstituted alkene. This is monosubstituted alkene. This one, let's say this is let's give a name. Let's say this is 1, this is 2. 2 is more stable than 1. Okay, let's look at the second one. The second one, actually they are the same molecule, but they are isomers, stereoisomer. This one, as you see, methyl and ethyl are on the same side. So this is cis, and this is methyl and ethyl are on the opposite side of the double bond. So this isomer is trans. We know that trans isomer more stable than cis isomer. Let's look at the third molecule. The third molecule I'm going to show on the structure. Here, let's say carbon. This carbon has this substituent, and this is CH2 as substituent. It's non-hydrogen. How about this one? This carbon has one hydrogen here and a CH2 group here. So basically 1, 2, 3 substituent, the first molecule. Let's look at the second molecule. Second molecule has carbon-carbon double bond, which has 2 hydrogens on this side and 2 carbons on the other side. So it is disubstituted. Let me write disubstituted, and this is tri-substituted, and tri-substituted is more stable than disubstituted. Basically, you can expect a similar question in one of our assessments in quizzes or in midterm or in final. Okay, let's move to the next topic. The next topic is electrophilic addition reactions of alkenes. This topic we have already seen in previous chapter. What is the reaction? This reaction, we have an alkene. An alkene reacts with an acid, HBr, sometimes it can be HCl, and what we generate? First we generate a carbocation, then the anion add itself to carbocation, and we form this addition product. Basically, alkene will act as a Lewis base because it's going to donate its electron pair. The pi electrons will be donated, and HBr is considered as Lewis acid because it's accepting electron pair. Okay, the reaction has two steps. The first step is formation of carbocation, and in the second step the anion here, the Br, bromide anion, is adding itself to the carbocation. Is the second step. The energy profile, this is the first step is highly endergonic step, delta G is positive. The second step is highly exergonic, delta G is negative for the second step, and overall delta G is negative, so overall it's an exergonic process. Okay, and similarly instead of HBr, HCl can also be added, so we are going to generate a similar product. Instead of Br, here we get Cl, 2-chloro-2-methylpropane. Also iodine can be added, but hydrogen iodide is not very reactive, so we use potassium iodide and phosphoric acid to add 1 part hydrogen and 1 part iodine. And a similar reaction here, instead of HCl or HBr or HI, we can add water. You can think of water as H. Instead of Cl we have OH, so we add 1 part hydrogen, 1 part OH. If you look at the reaction, we can like write a reaction here. Carbon-carbon double bond, and we are adding an acid, and we are forming here a carbocation. I'm going to add this hydrogen here, and this will be carbocation. And the reaction mechanism, electrons moves from pi bond to hydrogen, then the chlorine, this bond is breaking, so plus we have Cl minus. So when you look at this alkene, basically this alkene is not symmetric, but when you look at here, hydrogen is always adding itself to this carbon, not that carbon. In the incoming slides we are going to explain this phenomena. So when we react 2-methylpropene with HCl, possibly we can form 2 carbocation. So let's show it here. Let me use arrows. So I'm going to say HCl. So this bond will break, right? So possibly the hydrogen can be added to this carbon or the other carbon. So if we add the first carbon on the left side, we are going to get this carbocation. And if we add hydrogen to this carbon, it's possible we are going to get this carbocation. So basically we can get 2 possible carbocations, and the chloride anion as a nucleophile can add itself to this carbocation or to this carbocation, but experimentally this carbocation is formed and this carbocation does not form. So basically when you look at the products, this is not formed, or sometimes it is formed maybe 10%, maybe 5%, but exclusively this is going to be the major product. So when you have a reaction, and if the reaction can produce 2 possible products, the one that is produced in more amount we call major product, and the one that is not formed or formed little amount we call it minor product. So why this is happening? Before learning why this happens, we have to learn a rule which states which is Markovnikov's rule. According to this rule, it says that when we add an acid like HCl or HBr to an alkene, the hydrogen, here this one, attaches itself to the carbon with fewer alkyl substituent. Let's look at here. How many alkyl we have here? We have 2 alkyls. So let's write here 2 alkyl group. And how many alkyl we have? 0 alkyl groups, because it's all like it has 2 hydrogens and hydrogens are not substituent. So the bottom line here, the hydrogen attach itself to the carbon with fewer alkyl substituent. So it is attaching here, as you see, this is the major intermediate and this is the major product. It attaches itself to the carbon with fewer alkyl group, and the chloride is adding itself to the carbon with more alkyl group. So this rule is a little bit difficult to remember, so I'm going to change this rule into a new rule, which is not Markovnikov rule but Dr. Ibrahim's rule. What is Dr. Ibrahim's rule? Dr. Ibrahim's rule says that when we have an alkene, when we have an acid, hydrogen will be attached to the carbon of alkene with more hydrogen. So how many hydrogen we have here? 2. And how many hydrogen we have here? 0. So hydrogen will attach itself to carbon with more hydrogen, and the anion chloride, it can be chloride, bromide or OH, whatever it is, it will add itself to the carbon with fewer hydrogen. So hydrogen attaches itself to carbon with more hydrogen, the anion will attach itself to carbon with fewer hydrogen. So this rule is called Dr. Ibrahim's rule. Of course it's a joke, so there is no such rule, but I just changed Markovnikov's rule to another statement which you can remember easily. Okay, let's look at some other exercises. For example, let's do option B. In option B it says that predict the product of the following reactions. So here we have an alkene, right? So hydrogen, we are going to add hydrogen and Br, so it's an electrophilic addition reaction. So hydrogen will be attached where and bromide will be attached where? It's very easy. So let's look at, we have carbon of alkene functionality double bond. Which one has more hydrogen? This carbon has 0 hydrogen, this carbon has 1 hydrogen. So according to my rule, hydrogen will be added here and Br will be added here. This will be single bond. So that's the major product. The other way around is going to be the minor product. So let's look at this one. Here we have an alkene, we have water and sulfuric acid. It says that instead of HBr, H2O will be added. So we will add H and OH. So let's look at carbon with 2 hydrogen, carbon with 1 hydrogen. Of course hydrogen will be added here, and in this case OH will be added here, and this will be a single bond, right? And let's do this one. This is the carbon and this is the carbon of double bond. This carbon has 2 hydrogen, so this will be 3, right? And Br will be added here because we are adding HBr. Okay, let's move to the next topic. The next topic is carbocation structure and stability. In the previous examples, we have seen that we can form. So let's go here. We can form here 2 carbocation, and one is the one that gives us major product. The carbocation here is an intermediate. It's a tertiary carbocation. Why it's a tertiary carbocation? Because the positively charged carbon, let's look at here, positively charged carbon has how many neighboring carbon? 1, 2 and 3. So that's the reason this is a tertiary carbocation. And this one, the other possible carbocation that will form, but it is not formed or formed in minor quantities, this is a primary carbocation. Why? Because the positively charged carbon is next to just one carbon. So then let's go back to our discussion. Why we form tertiary carbocation and why we didn't form primary carbocation. As you remember in our previous discussions, if something forms more, or if something produced in more quantity in a chemical reaction, we always base our reasoning to stability. So the reason why we got tertiary carbocation, not primary carbocation, because tertiary carbocations are more stable, or they have less energy compared to primary carbocation. How can we understand the stability? Basically, if you look at electrostatic potential map of methyl and primary carbocation, a secondary carbocation, a tertiary carbocation, the positive charge density on carbon is less when we have a tertiary carbocation. Why it is this case? Because in the tertiary carbocation we have 3 neighboring methyl groups or alkyl groups. They release electrons through the positive center, so they a little bit neutralize the positive charge, or in a more correct way, the positive charge is dispersed when you have neighboring carbons. So here we have 3 neighboring carbons next to the positive carbon. Here we have 2, here we have 1, here we have 0 carbon. So here in the methyl carbocation, the positive charge is centered or localized. But when you place more alkyl groups or more carbons around the positive charge will be dispersed or delocalized. And when you delocalize a positive charge or a negative charge to more area, or if you spread more, it makes it more stable and it makes it less reactive. That's the reason why a tertiary carbocation is more stable than secondary than primary, and this effect is called inductive effect. So methyl groups or carbons around a positively charged carbon, they release electrons towards the positive charge. So basically this is called inductive effect or inductive stabilization. Sorry for that. Okay, so this was the last topic for this chapter. So this is your assignment. From chapter 7, these are the suggested problems, and also you can read the textbook chapter 7 except these parts. Thank you so much for watching this lecture.